We're going to take a look at section 7-2 and review it and learn about similar polygons. So it's probably a topic that you've heard of, and we're going to maybe go a little bit more in depth and really learn how we can discuss similar polygons and how we can decide if two polygons are similar. So let's go ahead and start with that vocab term. Similar polygons, or similar figures, we're going to use, have the same shape, but not necessarily the same size. So that's what's really important here. Same shape, but not the same size. If a figure has the same, or if two figures have the same shape and the same size, those are congruent figures. In this case, we're not looking at ones that have the same size. They do have the same shape, but not the same size. And when we talk about similar figures, we actually have a little abbreviation, and it's just kind of a one little squiggle or tilde. You can see it right here. That reads is similar to. So we could say triangle ABC squiggle is similar to triangle DEF, and we'll see that used throughout today. All right, so let's get a nice definition here. So we can use those ratios and proportions that we looked at in section 1 to decide if we have similar polygons. And if we know we have similar polygons, we can use those ratios and proportions to find missing lengths. So we're going to do both those concepts today. So by definition, two polygons are similar polygons if corresponding angles are congruent. I'm going to get my highlighter out. So my corresponding angles have to be congruent, and the lengths of the corresponding sides are proportional. Okay. Now remember in the last section we said there are a lot of right ways to set up proportions, and we're going to see that come into play big time here. What you write down might be different than what I write down, but we should still always come to the same conclusion. So corresponding angles are congruent, so all of your corresponding angles still must be congruent, sides must be proportional. And we'll look at that here in an example in a second. So you write a similarity statement with corresponding vertices in order, just as you write a congruent statement. So remember specifically back to chapter 4, but in the past, when we write two triangles or any sort of figures are congruent, we have to write it in corresponding parts order. Meaning, if I write ABC, then my other triangle, I have to have those corresponding angle to A first, corresponding to B second, and C third. When three or more ratios are equal, you can write an extended proportion. We looked at extended ratios in the last section. An extended proportion is similar. Set up your ratio equal to another ratio, equal to another ratio, equal to another ratio, and you can do that for as long as you want. Within this extended proportion, it does not matter what order you put each of those ratios. AB over GH could have been in the middle or at the end. Order doesn't matter. You can switch those around and still have equivalent proportions. Now, when we're looking at similar polygons, we talk about the scale factor. And a scale factor is the ratio of the corresponding linear measurements to two similar figures. The ratio of the lengths of corresponding sides, BC and YZ in this case. So BC is my right side, YZ is my right side. Or more simply stated, the ratio of corresponding sides is BC over YZ, which is 20 over 8, which reduces to 5 over 2. So our scale factor is 5 over 2 or 5 to 2. Different ways that you can look at that. So that's a lot of information. Just wanted to put that in there so you kind of have the bulk of this section in that one little paragraph there you can refer to. But let's break it down and let's look at all those pieces kind of individually here with some examples. So we're just going to start with looking at writing in corresponding parts order and understanding what that means. So I'm told here that triangle MNP is similar to triangle SRT. So I do have a picture here, but let's at first approach this as if we didn't have a picture. And I want to know what the pairs of congruent angles are. Without looking at my picture, I can just know that since my similarity statement is written in corresponding parts order, I can find my congruent angles. So the first angle listed of my first triangle M is going to be congruent to the first angle listed in my second triangle. So I know angle M is congruent to angle S. That's what corresponding parts order tells me. Same with the second. My second angle listed in my first triangle is angle N. So angle N is congruent to the second one in my second triangle, angle R. And lastly, my last two angles says angle P is congruent to angle T. Just like what we did when we looked at congruent statement for triangles. The way they're written matters. Now, this part's going to be new. Part B says, what is the extended proportion for the ratios of the corresponding sides? There are a lot of right ways you could answer this. I'm going to start with my first triangle, and I'm going to put those sides over my second triangle. You could flip it. You could put the second triangle first over the first triangle. It doesn't matter as long as you're consistent. Now, again, I could look at my picture, and I could say, hey, N, this left side, looks like it probably corresponds to RS, the right side. But instead of using the picture, I'm going to go back to my my similarity statement up here and list my first two sides, MN and SR. So my proportion of MN over SR is going to equal, now I'm going to list my second two sides, NP over RT. Again, always listing that first triangle first. If you flip it, always be consistent. And the last ratio in my extended proportion is going to be my first and last over first and last, MP over ST. So my extended ratio is what's written here. And again, you could write it in any order you wanted to. You could put the maroon ratio first and then the blue and then the purple, or blue then maroon then purple, or blue then purple then maroon. It would still be right. You could flip all of those. Remember how we looked at that in the last section? All of these ways that you can rewrite proportions to still be equivalent. So know that if yours doesn't look just like mine, that's okay. But just as long as you're consistent with whichever triangle you pick to be on top is the side that's on top for all of them. So knowing that they're similar means when you divide each of these sides by the first triangle divided by the second triangle for the corresponding sides, you should get the same scale factor or the same ratio when you simplify. So let's look at one more example. Here I'm not given a picture. I have a quadrilateral DEFG, and it's similar to quadrilateral HIJK. HJKL, excuse me, I was misreading that and I was confused for a second. All right, so again, start by listing the corresponding angles, or the congruent angles will be corresponding. So our first two angles are congruent, which means angle D is congruent to angle H. Our second two angles are congruent. Angle E is congruent to angle J. Our third angles, angle F, congruent to angle K. And our last angles, angle G, congruent to angle L. Just strictly taking them from that similarity statement. Then, if we want to write the extended proportion of the ratios of lengths for the corresponding sides, again, pick whichever one you want. One way to do this would be, just like I did in the last one, I would take the first two vertices to make side DE, put that over my first two HJ. Set that equal to, I'm going to move into the middle two, EF over JK. Move on to the last two, FG over KL. And then the first and the last, DG over HL. Order doesn't matter. What matters is consistency. I picked the first quadrilateral as my top side for all of those, and the second quadrilateral as my bottom for all of those. If you're having issues setting that up, let me know. I'll be happy to show you some more examples and go over that. But we don't just want to know how to understand corresponding parts order. We want to know how we can identify if I've got similar figures. So I'm asked here if these polygons are similar, and if they are, I need to write a similarity statement and give the scale factor. So remember your similarity statement, you have to be in corresponding parts order. So I've got these two quadrilaterals here, and when you're checking for similarity, it's going to be a two-step check. The first thing you want to do is check if all of your angles are congruent. Now in this case, I'm not given a congruent statement, so I'm going to have to use my best judgment, use the knowledge I'm given to decide which are my corresponding angles. Well, notice angle M has one congruent marking. That's going to be congruent to angle W, so M and W are going to be corresponding, and they're congruent. So angle M is congruent to angle W. I've got two congruent markings on angle J, which is congruent to angle T in my second quadrilateral. I've got a right angle for angle K, and I've got a right angle for angle U, so K is congruent to U. And lastly, I've got three congruent markings on L as well as V, so L and V are congruent. So these check out. I've got 4 angles in the first quadrilateral congruent to 4 angles in the second. My step 1 checks. I'm on the right track to having similar figures. My step 2, I need to compare the ratios of corresponding sides. So again, I don't have a similarity statement to look at to find my corresponding sides, but I'm going to use what I just found in my congruent angles to check. Well, since M is congruent to W and J congruent to T, then MJ has to be corresponding to WT. Okay? MJ over WT. Those are my corresponding sides. MJ has a length of 6. WT also has a length of 6. And then go ahead and reduce. 6 over 6 is 1. Always reduce. Okay? Now that we're in the process of checking. The next congruent sides, or corresponding sides rather, would be JK corresponding to TU. And again, you can pick these in any order. And let's check. JK has a side length of 12. TU has a side length of 6. And reduce. 12 over 6 is 2. Now, we could stop right here. I already know that my first side that I compared it has a ratio of 1. The second one has a ratio of 2. They're not the same. I'm going to go ahead and just quick list the other 2 ratios so we can see that, in fact, we have no same ratios. LM over VW is 24 over 14, which reduces to 12 over 7. And what's the other one? KL over UV gives us 24 over 16, which reduces to 3 over 2. So notice here, what's important is our reduced ratio. 1, 12 over 7, 2, 3 over 2. All 4 of those would have to be the same in order for my quadrilaterals to be similar. So since corresponding sides are not proportional, these polygons are not similar. So not similar. So since they're not similar, we don't have to worry about scale factor or similarity statement. Let's try another one. So I've got triangle ABC here, and I want to know if that's triangle to similar EFD. So step 1 said check the angles. In this case, it looks like angle A has 2 congruent markings, and so that's going to be congruent to angle D. Angle B has 3 markings, and so does angle E, so B is congruent to E. Let me try that again. It's a little hard to read. And angle C has 1 marking, as does angle F. So I do have 3 congruent angles. Corresponding angles are congruent. That part checks out again, just like I did last time. Now let's check our sides. So again, I'm going to use my congruent angles to determine my sides. I'm just going to start with my first 2, AB over the first 2 of my second triangle, DE. AB has a length of 12 over DE has a length of 15. And reduce 12 over 15, each can be divided by 3, and we get 4/5. Okay, so we're on the road to checking. I'm going to take my second 2, BC over EF. BC has a length of 16. EF has a length of 20. Both are divided by 4, 4 over 5. So notice so far, both have a proportion of 4/5. But I can't stop there. Just because 2 are the same, I've got to make sure the third is also the same. If I end up with the third not being the same, then I don't have similar figures. So all 3 need to be the same. So I've got AC over DF. AC is 8 over DF is 10. Divide by 4. Excuse me, divide by 2, not 4. 4 over 5. Notice here, when I reduced each of those ratios, all of the sides have a proportion of 4/5. So since corresponding sides are proportional, my triangles are similar. Since I got the same number and I have corresponding angles congruent. Now I need to write a congruence, I keep saying congruence. I need to write a similarity statement. So triangle ABC is similar to, make sure you're not using the congruent sign, just the similar to. Now, make sure that when you write your second triangle, you're writing it in corresponding parts order. So which angle is congruent to angle A? Angle D is. Which angle is congruent to angle B? Angle E. And F is congruent to C. So my similarity statement is triangle ABC is similar to triangle DEF. And then I wanted to include a scale factor. And your scale factor is whatever you get as a reduced value when you do your proportions. Now, here's what's important. Your scale factor needs to correspond to your similarity statement. So since I listed triangle ABC, or if you want to look at it, the first triangle first, I need to make sure that that's the number on top for all of my proportions. So that is what I did. So my scale factor would be 4/5. What I mean by that is if you were to write your similarity statement switched to say triangle DEF is similar to triangle ABC, you could do that. You could write either triangle you want to first, but then you would need to flip your scale factor. So then you would say triangle DEF is similar to triangle ABC by a scale factor of 5/4. Or if you want to write it, I'm using the colon, 4/5 in this case, or 5/4. So just make sure that you're being consistent. So if you're listing the left triangle first, then that has to be the top number on your scale factor. All right. Now, we've looked at how to use our similarity statements. We've decided if we have similar triangles. Now we're going to use similar figures to find missing sides. So here we're given that ABCD is similar to EFGD. So we're told that these are similar figures. We don't have to check it. We know it. I want to find the value of X, and then later I'm going to find the value of Y. So since we know the polygons are similar, we're going to have to use either the similarity statement or the picture to set up some ratios here. When looking for X, X is the length of FG. And FG is going to correspond to BC. And you can find that either by looking at your similarity statement, FG are the middle two over the middle two, or you can do it by just looking at the figure and seeing which two sides were going to be corresponding. Now, in the practice with our extended ratio, we set up all of our corresponding sides. In this case, I don't need to set up all of them. I just want the side that I'm looking for, which is FG, and I'm going to set it equal to, and this is going to be the trick here, always finding the sides that you know. When you're looking for a missing side length, you have to be given one set of corresponding sides that you know the length of both of. And that's what we have here. Notice length DE corresponds to length AD. I'm going to go ahead and erase that so we can see. Or here, I'll use a highlighter. ED corresponds to DA, and ED is 6 and AD is 9. So look for what you know the lengths of both of. So also you could see DG corresponds to DC, but I don't know their lengths, so that doesn't help me. I need to the ones that I know the lengths of both of. So I'm going to write, since I did the small quadrilateral on top, I'm going to write the small one on top, ED over DA. Okay, so being consistent. Now, let's use substitution and plug in what we know. FG has a length of X, BC has a length of 7.5. Set that equal to ED has a length of 6, DA has a length of 9. Now, hopefully you're seeing something similar to what we saw in section 1. We can use cross product property or cross multiply to solve. X times 9 is 9x equal to 6 times 7.5. So 9x, 6 times 7.5 is 45. So 9x equals 45. Divide both sides by 9. X equals 5. And that's what you're looking for here. If you wanted to check it, 5 over 7.5 Is that the same thing as 6 over 9? Go ahead and you can multiply 5 over 7.5 by 2 to get 10 over 15 to get rid of that decimal, and then reduce 10 over 15. You're going to get 2 over 3, just like with 6 over 9. You have that scale factor of 2/3. You found your missing side. Now, the second part down here says we're going to use the same diagram, and we want to find the value of y. So, especially when we're looking at the same diagram, I always like to stick with what I know. I could certainly use FG over BC. I could say 5 over 7.5, but I'm going to stick with the one I know. ED over DA. I'm going to say that that's equal to whichever one uses y, so I can solve for y. Well, y is EF, and that's going to correspond to AB. So again, small quadrilateral first, EF over AD. Oh, that's not right. AB, sorry. EF over AB, and then substitute in what you know. We know ED has a length of 6, DA has a length of 9, EF is y, that's what we're looking for, and AB is 5. And again, cross product property or cross multiply, 6 times 5 is 30, is equal to 9y. Divide both sides by 9. Y is equal to 39ths, but always reduce. We can divide each by 3, so we get 10/3. Y is the fraction 10/3. So that's using the cross product property to find a missing side length. Now this last part is the trickiest part. And you'll just have, I think there's just one of these on your homework. But it's an important concept to kind of go over. So it says your class is making a rectangular poster for a rally. The poster's design is 6 inches by 10 inches. So it's just a little design, less than the size of a piece of paper. But the space allowed for the poster is 4 feet by 8 feet wide. 4 feet high, 8 feet wide. What are the dimensions of the largest poster that will fit on the space? So what they're saying is, imagine that your design is about the size of a piece of paper. It's a little bit less than your computer paper. And we want to blow it up to fit under this poster that's 4 feet by 8 feet. But you don't want to mess up the proportion, right? You don't want to make it too long or too wide. You want to keep the proportions the same so it looks normal. We're not changing the look of the design, but we want it to fit as big as we can on this poster board. So this is also a 2-step process. And step 1, we're going to want to determine whether the height or the width will fill the space first. Determine whether the height or width will fill the space first. Okay, so this is going to be a check for both. Start by checking the height. And the height of our poster is 4 feet, but since we're working in inches with our original design, we want to convert that to inches. So 4 feet multiplied by 12 is 48 inches. So how many times should I multiply my design, which has a height of 6 inches, to get to 48 inches? So to solve that, we're going to do division. How many multiplications can I do to fit this 6 inches into the 48 inches? So 48 divided by 6 gives us 8. That means for the height, I could blow up my design 8 times. I can make it 8 times as large as the original one, and it will fit exactly as the height of the poster. So now let's check it for the width. The width of my poster is 8 feet. We want to convert that into inches, multiplied by 12. So my width of my poster is 96 inches. So the same question applies. If I've got a 10-inch design, how many times can I multiply or blow up that 10-inch width to fit into the 96-inch space? So we're going to do that. Same division, 96 inches divided by 10 inches gives us 9.6. So in order to fill up the whole width, I'd have to multiply my original design 9.6 times. So now we have to decide which scale factor am I going to use. For my height, I said I could have a scale factor of 8. For my width, I said I could have a scale factor of 9.6. So let's think about what this means. If I take my original design and make it fit the width, I would have to make the height 9.6 inches larger. Or excuse me, 9.6 times as large. That should not say inches on it. That's a scale factor, sorry. 9.6 times as large. If I make my height, if I take my 6 inches and multiply it by 9.6, I'm going to have a height that goes off of the poster board. It would be too big. So once I figure out the scale factor of each, I need to take the smaller scale factor so that I don't end up going off the poster. In this case, I'm going to use a scale factor of 8. So if I use a scale factor of 8, or I blow up my original design 8 by a scale factor of 8, it's going to take up the whole height. It won't quite take up the whole width of the poster, but that's okay. It's not going to distort my design. So the second part of this is actually finding out what those values are. So part 2, we know that the greatest height is 48 inches. So we already know our height is 48. So we need to find the width. And we said we're going to be using a scale factor of 8. So take our original width of 10 inches, multiply it by a scale factor of 8, and we get 80 inches for the width. So my design to fit under that poster, we're going to be 48 inches tall by 80 inches wide. So in this one, it's just a 2-step process. First, check to see which scale factor you use. How many times can you blow it up to fit the height? How many times can you blow it up to fit the width? Pick the smaller one so you don't end up going over your poster, and then find the remaining value. So to wrap up section 2, lots of times similar figures come into play with what we call a scale drawing. And in a scale drawing, all lengths are proportional to their corresponding actual lengths. The scale is the ratio that compares each length in the scale drawing to the actual length. The lengths can be used in a scale, can be different units. For example, a scale might be written as 1 centimeter to 50 kilometers, 1 inch to 100 miles, 1 inch to 10 feet, etc. You can use proportions to find the actual dimensions represented in the scale drawing. So this is something you've seen before. This is what happens on maps. Obviously, if you're looking at a map, you're not looking at the actual distance between, let's say, 2 towns, but it should be a scale drawing. So at the bottom of each map, there's going to tell you a scale. It might be 1 inch. Let's use this one here, equals 100 miles. So if you measured with a ruler, let's say how far it is from Colorado Springs to Denver, multiply that by your scale factor, that should tell you the actual distance in miles using a scale drawing. So it's something you've probably had some familiarity with. If you have any questions on these, shoot me an email and we will set some time to go over them.